Now, there's a couple of things I do want to point out to you about how to use Zoom in case you have never used Zoom before. And just the first thing is that I have got everyone muted except for me right now, and I've got, and it looks like everyone's video is off as well, but then that's fine. But if you choose to speak up and ask a question, you can do so by just turning off your microphone and asking a question. That's fine. Or let's see here. You'll find a chat option underneath the More menu, which is on the far right side of the menu bar, and you can enter a chat question in the chat box as well if you have any questions that you want to ask throughout the session today. Just go ahead and enter your questions as you think of them, and I will stop periodically and check the chat box and see if there are any questions that I need to address. And so let's see, today is the Data Management Best Practices class, and this is a follow-up to the Data Management Plans class. And so today's class is more about how to manage data on a day-to-day basis and some tips and tricks on managing data with some commonly accepted best practices. And so we'll get into some of that stuff later, but just wanted to do a brief introduction. My name is Chris Eaker. I'm the Data Curation Librarian. My office is in Hodges Library, and you can always reach me via email at ceaker@utk, and I'm usually pretty responsive to email, unless I'm traveling, and at which point you'll know that by a autoresponder. But today's session will also be joined by Joy, and she is head of our cataloging and metadata department here in the library, and she will help me out on the metadata section that we'll get to later on today, later on this morning. So you can also reach her via email, apanigab@utk.
Hello, I just wanted to say hi.
Thank you, Joy. So let's see. Let's go ahead and get started here. All right, so today's outline, let me see if I can do something with this. There we go. I'm going to move my menu bar out of the way so I can see what I'm looking at here. Today's outline, we're going to start off by just talking a little bit about why it's important to manage data well. And one of the main reasons we want to manage data well is because data sharing has become an important part of our work as researchers. Most of the grant funders that you deal with today are requiring that data be managed well throughout the project and then placed in a location where it can be shared and made public with other researchers. And unless there is a legitimate reason why that cannot be done, in which case you would want to describe it and explain why that's not possible within your data management plan. But we're going to just go on the assumption that you're going to be sharing research data, and so data management best practices are important in that regard. It's also very important to you as a researcher just to make sure you have good, clean data, and it helps you understand what you're doing and follow and be able to find what you're looking for when you need it. We'll go into some tips and tricks on data entry and manipulation and some best practices that you want to be aware of while you're in data collection mode. And then some ways in which we can ensure quality control and make sure that the data are clean and free of errors. Then we will get into some best practices for backup, making sure that you're backing up your data regularly and so that you don't lose it in the event of a malfunction of equipment or some other reason. And then Joy is going to chime in with some some about metadata and why metadata is so important, and then some examples of some dataset metadata. And then I'll finish up with some data citation principles and some best practices there. And so again, if you've just joined before or since I said this, in the bottom, in the far right hand side of your menu bar, you'll see a more menu, and you can choose chat if you have a question for me. And I see that there's already one question for me, but I'm going to hold off, and I'll get to that at the end or later on today. But if you have a question, just enter it in the chat and I'll get to it. So why do we want to manage data well? Well, it's good data management best practices are helpful in making sure that you have a well-organized data set. It also supports reproducibility of data, which is a hot thing today. Funders especially, and journals want to make sure that the research they publish and the grant funders support is reproducible. And so data management supports that. Version control is also important when you're dealing with multiple versions. You want to be organized about how you maintain versioning. Well-managed data helps with making sure your data is high quality. And data itself is a very valuable asset, so we want to make sure that it's managed as the valuable asset that it is. It's not only valuable to you as a researcher, but to your discipline and to the university. Data management best practices help ensure that your data is accurate and has high integrity, and therefore is more suitable for data sharing at the end of your project, or at any point really. But we're talking about when the project's finished and you've got a data set that is finished and can be placed in a place where it can be shared. So if data are well organized and documented well with good metadata, and then preserved in a place where it is accessible, like a data repository, and it is also verified that it's clean, accurate, and valid, then the result is that you have a high quality data set that's easy to share and reuse by other researchers within your discipline and in other disciplines. It can be cited by others and reused, and adds credibility to you as a researcher. And then overall, it saves money by reducing duplication of efforts, by allowing other researchers to reuse data that they need and then do not have to recreate or recollect. So we're going to get into some of the reasons why data sharing itself is important. It requires a lot of effort, of course, and it does require some resources, and quite frankly, it requires you to have faith in other people and other people to have faith in you as a researcher. But there are benefits involved in sharing data for the public, your research sponsor, and your research community, and also you as a researcher. So benefits to the public include helping the public and local governments and state governments in planning things, economic planning, land use planning, environmental planning, etc. It also helps the public make social choices and how they would want their tax dollars to be used, and also education options for their own family, and just simply helping them make personal lifestyle choices for their health and their nutrition and their recreation options. And the more data that's available for them, the better they are informed and can make these choices. To the research sponsor, organizations, they want to make sure that they maximize the value of those research dollars that they're giving you, because it is, unless you're dealing with a private foundation, but even they want to make sure they maximize their value. But the public research funders are giving out tax dollars, so they need to make sure that they are using those tax dollars wisely. It helps to verify the performance metrics and outcomes, and allows new research to be spurred. Increases your return on investment, or the funder's return on investment. It helps to advance your science overall, and just reduces data duplication and therefore overall cost of the research. And to your research community overall, It's always important to build upon the work of others. That's of course what you do all the time, and thereby when you have additional research data available, you can more easily build on the work of your colleagues. Helps you to perform meta-analyses if you choose, or someone to do that with your research data and research data from other projects as well. And then it's always good to share your resources with others and perspectives with other colleagues. And so by sharing your research data, this is supported as well. Additionally, to the research community, by increasing transparency and reproducibility and comparability of results, then your research is stronger. It helps you expand methodology assessment and recommendations and improvements. And it also helps when you are supporting new researchers, or as a mentor or as an advisor. When you have data that you can reuse, you can educate them in the most current significant findings within your field. And then finally, to you as a researcher, there's the benefit of additional recognition by making your research data available. When you make it publicly available, it improves your data quality, because the more eyes that are on a data set, of course, the higher quality it becomes, because errors are found and errors are corrected. And it helps you to have greater opportunity for exchange with other researchers, in addition to just collaborating with them on research. By sharing your research data, your connections are improved with researchers across the world within your field. So just in a kind of a high level sense, we'll go through just some broad steps about making data shareable, and as we go through the presentation today, we'll kind of dive more deeply into these different things. So to make data shareable, we want to make sure that first we have robust metadata that is discoverable. And within that metadata, which is descriptive information about your data set and your project, you want to make sure that your geographic and temporal coverages are clearly defined. You want to make sure that if you are using a discipline-specific schema or a discipline-specific vocabulary, that you are using those and that they are clearly defined and utilized properly, and that you describe all the attributes that you're using within the data set clearly. You also want to make sure that you have archival and reference information clearly defined. So I would recommend you always include a suggested citation to your data set whenever you make it publicly available, or at any time when you share it with others, even if it's not public per se. If you share it with another researcher, just even via email, always include a suggested citation so that they can cite it. And include a persistent identifier, such as a digital object identifier, if it's possible. And I show a data citation example there, which I've obtained from the Dryad digital repository. Dryad's a data repository that archives research data from a number of different journal publishers. And you can see that the citation mimics that of a citation for any research article that you would cite within your papers. And this one includes a DOI at the end. And so what that DOI will achieve for you is locatability. If someone has that DOI, they can always locate your data set very easily. Always want to make sure that all your contributors within the project have reviewed the metadata and made sure that it is complete, and that the organization that you're working with has been identified accurately. Are your processes and whatever you've done to analyze and process your research data, are they described accurately and thoroughly? Are your contributions and other contributions adequately identified? Has your PI, if you're working with a different PI, reviewed and made sure that everything is complete? And is your funding organization also properly recognized? You always want to make sure that they're identified. And then if you've got all that done, then of course you want to make sure that your data is in a place where people can find it. And in this case, a data repository is really a great option. And just some examples for you, there are discipline-specific data repositories that you can choose from, and some examples here are the Knowledge Network for Biodiversity for the biological sciences, Long-Term Ecological Research Network. The LTER network is a good one for ecological research. There's an archaeological data repository called TDAR, and then there's the Inter-University Consortium for Political and Social Research, which includes a lot more than just political and social research, but it's a very strong social science related data repository that we at UT subscribe to, are members of, and we therefore anyone affiliated with UT can both access research data from this repository and also deposit data within this repository. Now, ICPSR also provides public access data that anyone, even those who are not members of the consortium, can access. But the benefits of using ICPSR as a member is that the research data is curated, and the metadata is checked for accuracy, and is also, they'll actually improve the metadata that you submit, and kind of a back and forth discussion with you. They will make sure that it is complete. And then there's also institutional repositories. You've probably heard of our institutional repository called Trace. Trace is it includes lots of things: articles, electronic theses and dissertations, posters, and it also can accept and does accept research data. We do have some research data sets archived in Trace. And other universities who have institutional repositories may not accept data, and many do, but some may not, and you just have to check if you're at a different university in the future. Theirs may not accept data, but ours does, and we can always work with you in importing and archiving data within Trace if that's what you choose to do. There's also a resource I wanted to bring to your attention called the RE3 Data Registry of Research Data Repositories. You'll see you can just go to that URL, re3data.org, and search via topic, by discipline, by content type, and all kinds of different ways to find research data that are research data repositories that might work for your research data. If, for example, you choose not to use Trace or some other repository that you're aware of. So just check RE3 data out when you get a chance, and see if you find one that would be a good fit for you. Before we move on, I'm going to check the chat just to make sure there are no additional questions that I need to address, and I don't see any. So just as a reminder, please put your put your questions in the chat if you have any as we go along today. And so let's move on to some data entry and manipulation topics. So the goals of the data management best practices with regard to data entry are to create data sets that are valid. In other words, that they actually measure what you're trying to measure, and that they're organized and they're easy to use by not only you and others in your research group, but also others outside your group that you might share that data set with. So I'm just going to go through this example of first of all, some poor data entry techniques, and then we'll talk about how they could be made better. So let's see here. Let me get my highlighter or my laser pointer. Here we are. Well, where'd it go? There we go. All right, so this is essentially a data set that it looks like researchers collected some data on different organisms or different species within some different sites, and it looks like they've collected it within 3 different blocks of data. Perhaps these are three different days in which they collected data. So the first thing I wanted to point out is that the dates are in different locations. You can see that the date here is in a column by itself, and then the date in this other table is in the heading, and then it's also in the heading on the bottom table as well. Another thing you'll notice is that the species is labeled differently. In this top left block, you'll see the species is a column labeled species, and in the next block, it's a column labeled rodent SP. So that's another inconsistency. What else do we see? The weight is located in the last column here in the top right table and labeled as weight. And then this bottom block of data, we see it's labeled as grams. So that's another inconsistency. So you've got the location of the data information is different on each block. It's also an inconsistent date format. In the top left block, you have dates 2/13/2010, and then you have Feb-10. So these are all inconsistent. And then the very last one, you've just got a quotation mark to supposedly indicate that it's the same as the one above. And then over here, you've got the date in the heading, and it's just 3/15/2010. And then the bottom section, you've got a third different type of date format, 10-APR-10. So these are all very inconsistent. The column names are inconsistent, and then the order of the columns are all different. So there's no consistency from one block to the next. What else is a problem here? We've got the sites are labeled incorrectly. You've got deep well with no space listed. You've got deep well with a space. Then you've got Rio Salado, and then Rio Salado with no space and a misspelling. And so there's just some inconsistencies there. Another thing you find is that the mean of the weights is listed under the same column with the weights, and then the label for that mean is listed under the column for species. The weights themselves contain both numbers and text. So how do you average how do you take the average or any type of statistical measurement of 12, 91, and escape less than 15? It's just not possible. So there are the problems here. Site spellings are different, capitalizations different, spaces are here, in some places they're not, etc. So how can we make this data set better? Well, by combining these 3 blocks of data within one block of data with consistent headings and consistent terminology, we come up with something like this. You have the date, it's all in the same column and the same consistent format. You have the sites that are all consistently labeled. The plot type, the species type, or the species type look like they are identified by some sort of code or abbreviation. And then you've got all the weights in numerical format with 1 decimal point. Now, one thing I would have done differently is I would have indicated what the units are on that weight, but that could also be indicated within your metadata somewhere. But it is always helpful to put it right there with your heading. You have whether or not this is an adult or a juvenile. In this case, you have Y for yes, it's an adult, or J for juvenile. Another thing I would have done differently is indicate just Y or N, whether it's an adult or not, as opposed to yes versus J. And then they have a separate comment column if you have additional information you want to indicate about different data points. So those comments are not built in elsewhere within the table like they are kind of in the other tables, the example we saw. So just some best practices here. make sure that you have descriptive column names in your spreadsheets. And so the first example, soil T30, without any additional information, you may not know that that means the soil temperature at 30 centimeters below the surface. So you could think that that's actually the temperature is 30 degrees Celsius. So this other, let me get my highlighter back. This other file name here is much more descriptive and therefore is more easily understood. And then species-code, it's more appropriate to use an underscore as opposed to a dash because it's best to avoid these special type of characters in column names because some software may interpret them as operators, and therefore just avoid it and use an underscore. And then descriptive file names. Mammal data -.csv would be much more descriptively described or descriptively shown as field visit 1 underscore small mammal data underscore the date. And I wanted to point out this date format, which I'll talk about a little bit later. The date format is in the ISO standard datetime format, which is a 4-digit year, a 2-digit month, and a 2-digit day, separated by dashes. So in this case, in the file name, it is acceptable to use dashes, whereas where I described earlier in the column names within the spreadsheet, it is better not to use dashes and to use underscores instead. And just as a reminder, if you come up with a question, if you have any questions, please put them in the chat. Another best practice when using data entry in Excel, or any other spreadsheet for that matter, is to enter complete lines of data at all times. So in this case, you see that there are empty rows in the first 6 columns, it looks like. So if you just a person looking at this could understand what this person was going for. In other words, these next 3 rows after this first data entry is probably the same data on these first 6 columns, and that makes sense to you as a person, but it doesn't make sense to a software that's running calculations. But especially you run into trouble when you try to sort this data. For example, let's sort this data on the species column, which is column G. Well, then you end up with a bunch of white space in your first 6 columns, and you don't have any idea what data go with the rest of the columns to the right. So always enter complete lines of data when you're entering data within a spreadsheet. Some additional best practices: if you have missing data, for example, you don't have a piece of data to enter within a cell, is you can leave it empty if it's a numerical value. You can also put some sort of distinct value, such as 9999 or negative 9999, to indicate that there's obviously a missing value. If you have a text field, you can always enter NA for not applicable. And then when you create your metadata, you can describe what those values mean so that people understand it. And then if you have additional information you want to describe about a data set, about a specific entry of the data, you can always add a data flag, which in a separate column, which in this case you see that this M1 flag indicates that the data was missing and no sample was collected. And then if you have E1, in this case, you see that it was estimated. Now, when you enter data within Excel, Excel is a pretty handy tool, of course, but it sometimes will cause trouble because it doesn't enforce any rules on you unless you tell it to enforce some rules on you. So, for example, on the data set we saw before, we saw some species were entered in all kinds of different ways, and Excel didn't care whether or not you wrote wrote it correctly or incorrectly. So one of the tools you can use within Excel is the data validation tools. And so, for example, on the species, like the species column here, it's best to use a list data validation tool where you can pre-describe the species that you want to be able to choose from, and then you select that list from the data validation tool window. And within that, so when you get to that cell, you'll have a drop-down menu, and you can choose a predetermined list of species or whatever the case may be in your case, and that will cut down on errors in typing and inconsistencies between one person and the next when there are different people entering data. So that's one tool that Excel provides to make your data cleaner and more accurate. Another thing is the numbers, and we saw that Excel will let you enter anything within a cell, numbers and text within the same column. And in this case, the height column obviously should be a number, but unless you tell Excel differently, it'll let you put text in that column as well. So another tool that you would want to use is it's also a data validation tool, but it allows you to hardwire what types of numbers must go within a cell. And in this case, you can tell it that this is going to be a decimal number, and it's going to be between 11 and 15. So you might know for a fact that the number is always going to be between 11 and 15. So you want to make sure that those limits are set so nobody can enter something outside of that. And then if someone does try to enter a 20, they'll get an error message that says you've entered an illegal value. And as well, if someone tries to enter some text within that cell, they'll get the same type of message because it cannot accept any text. So it's always best to think through these kinds of things with regard to your data, and to make use of these data validation tools within Excel when you're creating a data set. So just wanted to briefly discuss some of the differences and pros and cons with spreadsheets versus relational databases. And but before I go to that, let me back up, and I think I saw a question come in. Let me see what that question was. When choosing file names, is there a limit to the number of characters? I know there are backup programs for external drives that will not include files after a certain length. Does this become irrelevant once it's in a repository? It's going to really vary on the type of software that you're using, whether or not there's a limit. I'm sure that there is an upper limit at some point, but I don't know what it is, and so I can't really I can't tell you. But I would keep your files short enough I would be descriptive enough within your file so that you're describing what needs to be described within the title, but try not to get overly long. I think if you stuck with something like 128 characters or less, you'd probably be okay. But modern day computers are obviously more capable of handling longer file names than old computers were. But just to stay safe, you would want to keep it probably 128 characters or less. All right, so let's move on now to the differences in spreadsheets and relational databases. Spreadsheets are obviously great for creating charts and graphics and calculations. They run calculations very well. They create charts and graphs very easily. They're very flexible about what you can put within the cells, which is a good thing and a bad thing, as you saw. They don't force you to do things a certain way. They also will allow you to sort columns independent of one another. Current version of Excel does this better, though. It does ask you if you want to expand your selection to include the entire set of data if you try to sort a column before you actually do it. But you can also say no and sort it independently if you really want to, and so Excel is not going to stop you. It's very easy to use. Most people have a lot of experience using Excel, and therefore typically go to it as a first choice when they're dealing with numerical data sets. But Excel can get unwieldy as the data sets grow. So just keep that in mind. Now, some of the differences in that with relational databases, that they're very easy to query and select data or pull out portions of the data, or if you want to run analyses on just different parts of the data. You can also type the field, which means you are able to hardwire into the field whether it's going to be an integer or a decimal, or it's going to be just text, and you can also say text can only be 20 characters or less, etc. You cannot sort columns independent of each other. But on the downside, they do have a steeper learning curve if you're not familiar with relational databases. So I'm just going to go into a little bit about what relational databases are and how they're used. They are a series of tables containing information that are related to one another by a common ID or a common piece of data. So you see here we have three tables. The first table is information about the sample sites, and this is just a continuation of the previous examples that we've been looking at. So it's got all the information about the sample sites within this one table, and then the middle table contains everything about the specific samples that you're collecting, and then the third table contains all the information about the types of species that you would be collecting data for. Now you see that they are connected, though. In the sample sites table, there is a site ID, and that site ID is connected with the samples table, and so that ID is what connects these two tables together, the sample sites and the samples table. So that's the relationship between those two tables. So that's where we get the name relational database. And then the species ID from the species table is what relates the species table to the samples table. So you'll see that they both have the species ID listed. So that's how they're related to one another, and that's how they are able to pull data from other tables when you run queries. You have explicit control over the types of data that you put in. So for dates, you can tell it it's just going to be a date. It's going to be nothing else. For sites, will be text only. Height will be real numbers only. And then you can tell whether or not the organism of the plant that you're looking at, whatever, will be a flowering plant, yes or no, and it can be anything with a binary, yes or no. And so there's relationships between the tables, which I showed you earlier, and that's the ID. For example, the site table is up here on the top right, which includes the site letter A, B, or C, and then the latitude and longitude of those sites. And then that site ID, the A, B, or C, is also within the top left table. And that's how you're able to pull in data about the sites, like the latitude and longitude, into another table by running a query. So you can combine those two tables, and that's the example on the bottom where the species and the date and site are combined with the latitude and longitude from the sites table, and it creates another table that's independent of those first two tables. And then you can use that table to run additional queries or calculations just using that combined table. So that's one of the benefits of a relational database. It also contains the ability to run queries using structured query language, which is a command language. So you see this top table is called soil temp, which includes information about information like the plot that came from, the treatment, whatever that is, the sensor depth, and the soil temperature. So you're able to run a query and, for example, say, I want to select the date, the plot, the treatment, the sensor depth, and the soil temperature from the soil temp table, which is the top table, only where the date equals February 1st, 2010. So it will bring back only those data points that contain that date, February 1st, 2010. You can also run it by saying, I want to select everything from the soil temp table where the treatment equals N and the sensor depth is 0. In that case, there's only one case where that meets those criteria, and it's the last line of that soil temp table, and it brings that back as its own table as you see at the bottom there. You can get very complicated in your SQL command strings, but you can do quite a bit from just a very basic knowledge of SQL. Additionally, relational databases and Microsoft Access is one of ones that you might want to use. It provides the ability to enter data in a form. Therefore, you don't have to actually enter it within the tables themselves. You can enter it within tables, but it definitely makes it easier to do it in a form. And so you can build these forms within Microsoft Access fairly easily, and then it allows you to enter that data pretty easily, and then it feeds it into the tables. So just in summary, be aware of the best practices that I discussed when you're designing what type of file structure you want to use, if you want to use a spreadsheet or a database, and how you would build that spreadsheet or database. Choose the method that allows some validation when you're entering data. Excel will not do it unless you tell it to, so be aware of the data validation tools you have available within Excel and use them properly. And also, if you decide to use a relational database, that kind of thing is built in, so you're good there. And if you feel like it's worth your time, I would suggest learning how to use a relational database, because if you're dealing with a data set that's large or complex, that has some real benefits in using those and using a database over a spreadsheet. Are there any questions about spreadsheets or databases? I don't see anything on the chat, but go ahead and enter it if you have some, and I'll come back to it later if you do. Let's talk a bit about quality control and quality assurance things that we can do. Just be aware that while you're entering data, there's different types of errors you can commit. Errors of commission, which is where incorrect or inaccurate data have been entered. And an example could be a malfunctioning instrument spitting off incorrect data or a mistyped data. But you can also make errors of omission where you've just not entered data where you should have entered data. And it could be by human error, or malfunctioning instrument as well could do the same thing. So there are two ways that you can make errors, and just if you're aware of them, it helps you to remember to look out for them. So before you start collecting data, it's better to sit down and think through how you're going to do it. Define some standards that you're going to use beforehand, and then make sure you enforce those standards while you're collecting data. Think through what type of formats you plan to use. Are you going to have any specific codes that you want to make sure you use? So think through the codes, identify them, and record them somewhere where everyone can see. What kind of units do you plan to use? And what metadata do you think is important to record as you're collecting data? And just make sure that there is someone assigned to ensure that data collection and quality control and quality assurance happens, because if nobody is assigned that specific responsibility, then everybody thinks that everybody else is taking care of it, of course, and then nobody takes care of it. So there's some techniques that you can employ while you're creating data sets and entering data that will help you make sure that you minimize chances for error. You can enter data twice. The double entry technique is when data is entered by two people separately, and then you can compare their two data sets and find errors, and that will help you to identify places you want to go back and double check and make sure that which one of these is correct, and that will eliminate chances for, or not eliminate, but reduce chances for error, of course. You can make a recording of yourself reading the data and then read that data back and transcribe it from the recording, and that eliminates the chances for transcription errors, and it helps you to just the connection with hearing it and then writing it is less error prone than the connection of reading data and trying to write it. There's something about that, the difference there. You can use a text-to-speech program to read data back to you after you've input it, and then you can double check it with what you've got in another location, and you can compare the two. Make sure you design your storage system well and minimize the number of times when you must enter the same piece of data repeatedly. That is one of the benefits of a relational database. So you just enter data once, and then you can reuse that data many times from that point. Use consistent terminology from one place to the next and from one person to the next, and make sure that each cell of data only contains one piece of information. And that's called atomization. So just want to make sure that it doesn't contain text and data, or text and numbers in the same cell. You want to put just text in text cells and numbers in number cells. And then always document any changes that you make to data. Like when you collect data in a raw format, then you go through and clean it up and maybe do some transforms to it. So you want to make sure you document these things that you do to the data set. So if you need to back up and redo things, you have that documentation, and you're able to reproduce what you've done. And then it avoids duplicate error checking, and allows you to undo things if necessary, because you've got a good record of what you've done to get to the point where you are. Always, of course, make sure that you have data lined up in the proper columns, and that you don't have any missing or impossible or anomalous values within the data set. And then you can also perform some statistical summaries on the data, like some averages, some standard deviations, things like that, just to kind of see what, if anything, jumps out as anomalous to you, and it could help you identify data errors. If you have data that can be plotted, it is a good idea to plot it and then look and see what shows up on the graph. And if you've got an anomalous values flying out in space, like this example, you want to go back and look at it and see, is this an outlier that you want to maintain, or is this an error in your data set that you need to fix? An additional way to do it is if you have a graphical component to your data, like if there's coordinates involved, then just plot the coordinates on a map and see what you get. And if you've got all your data is up in that the Rocky Mountain chain, and you've got one data point often spaced down here in the Andes mountain chain, then you've got a problem, because most likely you've made an error there. So just overall, be aware of the errors of commission and omission and the ways in which those happen, and so that you can watch out for them. Always execute your quality assurance and quality control strategies that we've discussed, and during your data entry, and then visualize data if that will help you to identify any things that might look out of place. So if there are any questions about the quality control and quality assurance, please sure to enter them in the chat, and I will get to them. Now I want to address backup of your data sets, because it's very important that if you've got all this good clean data, that you've made sure it's all clean and accurate. You don't want to make sure that you want to make sure you do not lose it by having a good backup plan in place. So there's a difference between backups and archiving that I want to address briefly here. Backups are periodic snapshots of your data that you put in another location. They're usually copies of the files that you're actively using, and they're performed on a regular schedule. Whereas archiving is intended to preserve a certain version of a data set in perpetuity. It's usually the final version, but it can also be data sets at versions at specific project milestones that you want to maintain. So if you're collecting data on a daily basis, then you may want to set up a backup plan that creates a data backup on a daily basis, and may or may not overwrite the previous day's version. It's up to you. And then when you get to a point where you say, okay, this is a specific milestone of my project, I've gotten to the point where I've got my data in a clean point, and now I'm ready to start analyzing. Well, I want to now archive the data set before I start doing analysis and transforming data in other versions possibly. So that's the archive that you would create, and you would maintain that version in perpetuity. So it's always a good idea to have multiple copies of your backups and your archives in case one copy fails. So the reasons we want to make sure that we perform backups regularly is, of course, you want to limit or negate the loss of any data, because you put a lot of effort into collecting that data and you don't want to lose it. You save time and money and productivity when you have backups that you can always go to if you lose data. Prepare for natural disasters or disasters within your own lab or your own computer. Your hard drive might fail. I mean, there's any number of things that can happen that could cause loss of data, including just accidentally deleting a file. I've done that before. So backups help mitigate that risk. If you need to reproduce results, then you've got data you can go back to and reproduce. You may need to respond to a request for your data by your university, by your funder, any number of reasons people may request data. And so if you have a good backup system in place and archives, then you can always go back and find it. Then it helps eliminate or limit, that is, your liability as a researcher if you if legitimacy of your data is ever brought into question, then you've got something you can go back to and limit your liability. So data preservation is really another level on top of backups and archiving. It does include those tasks, but it also includes things like data conversion from one format to the next, reformatting data. As file formats might go obsolete, you can reformat a data to a newer version and maintain accessibility. And then there's also data rescue, which is if you've got a hard drive that's failed, there are data rescue services where they can actually recover that data, or at least attempt to do it, and recover data from a failed hard drive. And so these types of things, conversion and reformatting and rescue, are all part of data preservation, which is a kind of a broader issue than just simple backups and archiving. So just some best practices which help to help the archiving and backups. If you use non-proprietary standard formats for your files, then you minimize the risk that your data won't be readable in the long term, because file formats do go obsolete, and from time to time you may lose accessibility to your data. So it's best if you have textual documents, just simply save them in a TXT format, which is a standard open format. Spreadsheets with numerical data can be saved in a CSV file. Digital images can be saved in a TIFF format. Also, relational databases can often be exported in an XML format, and XML can then that XML format can then be re-imported within to another spreadsheet version if that is necessary. And XML is an open format that is essentially just a fancy text document. So you're not going to lose access to that XML file. And if you're using proprietary software or instruments within your labs or your research groups, then investigate what types of formats they might be able to export, and see if there's some sort of open non-proprietary format that they can export to, and that would be a better option for your long-term preservation of that data. So if that's possible, then that would be the better option than trying to preserve the non-proprietary format. Also, make sure that you version your files properly by indicating in the file name what the version is. And then remember the file naming conventions that I talked about earlier, and there's a few examples here I wanted to point out. So the this is about the date time format that I wanted to point out. So this first file name you can see is it's just, you don't know whether or not this date is April 13th, 2012 or December 4th, 2013. So it's best to use that standard ISO date time format, which includes the 4-digit year dash 2-digit month dash 2-digit day. So you always know that you've got December 4th, 2013 in this case. If you want to get really detailed, the ISO format also allows for time and time zone to be entered within the file name. So if that is needed, you have the ability to do that. You might be collecting data on a continuous basis and want to mark actual different hours throughout the day, and that is possible if you use that ISO format. So create a backup plan that clearly identifies the roles and responsibilities of who's going to make sure that the data is backed up on a regular basis. Always indicate where the data will be backed up and how often they will be backed up. How do you access the files where they're backed up? And then you can also, your backup plan should talk about the types of file formats that will be used in your backups, and then any policies for migrating data to assure that you're not going to lose it based on changing formats or file obsolescence. Review that backup plan on a regular basis to make sure that you don't need to make any changes, and then and make changes if you do. Always update it as you need to. Now, before I move on to metadata, I think there was a question regarding OneDrive that I saw earlier. In the last session, I'm assuming the data management plan session, you were talking about sharing data using OneDrive. It appears that only works if your collaborators are at UTK. Do you have another suggestion? As far as I know, you can request from OIT that your collaborators at other institutions be given a OneDrive account, or at least some sort of OneDrive login that they can use. So double check with OIT. The best way to get in touch with OIT is to use their help desk. You can do it by phone, by email, or walk into the help desk in Hodges Library on the second floor and talk to them about getting a login for collaborators for OneDrive. If that doesn't work, I'm pretty sure that they do allow that, but if it doesn't, let me know, and then I can investigate further. All right, at this point, we're going to go into the metadata section. So this will be Joy taking over, and I will go ahead and change access or change control of this presentation over to Joy. And Joy, I will let you take it over. Okay, we can hear you now. I just unmuted you.
Yeah, I can. Okay, thank you. I can't find my other button, but that's okay. Well, thank you for letting me join you, Chris. So my section today has to do with my work as metadata and cataloging department head. My name is Anjali Panikabut Roberts, and I work at the UT Libraries. Chris, I can't really. Just a second. I can do remote control. It won't let me. Let me try. Okay, here we go. Somehow I couldn't get the remote control, Chris.
Okay, if you want me to go ahead.
I have to request, maybe I have, right now it say I have the remote control.
If you want, I'll just go ahead and move the slides for you. Just tell me when.
Let me try again. So if I use the cursor, okay, here we go.
Okay.
So is that from my actions? Okay, oops, it went over. somehow. Maybe it has a slow reaction. Just a second. Let me go back. Okay, I think I'm okay now. So Chris talked about how you need to create your data, but the next step is also important for your data management to apply metadata to your data set. But why is it so important then? Because metadata is a part of your data reporting, can be to your agency, to your discipline database that need both the data and the metadata. So metadata is really about data. It tells you, for example, who create the data, what is the content of the data, when were the data created, if you have the timestamp, you want to add that, where is it geographically, if you have geographic location, you need latitude and longitude so that you can plot on your map. How were the data developed? What's your data collection method, data analysis, and population, and so forth? And why were the data developed? And sometimes it also asks a right statement, who own the rights? If other ones to use your data, how do you get the permission to use your data? So in general, metadata is greatly minimize the duplication of effort in the collection of if you have the expensive digital data that at the international level, you can really need to create the metadata for sharing and fostering the sharing of this digital data resource. Sometimes it's also important for describe the data for metadata, for meta-analysis if you have other people who want to query your data with different research questions. In the modern time, we also have metadata that can facilitate your data visualization, and also if you have researchers identifiers, it can also help you with cross-linking and sharing your data in your faculty portfolio, in your funding database that you are a member of. I try to move again. Okay, so metadata in real life, we have some example that if you play music, you can see the song list and the composer, the musician. For nutrition fact, you have calories, ingredients. So these are metadata in real life. In the libraries, the most common metadata you see every time you use the library is the library catalog information. You have authors, title, the publication, publisher information, the data publication. So your data set metadata will be similar. You will have the author's name, title of the data, and you can have other specification, like I mentioned earlier, the rights and so forth. So you can you can create a subject of the metadata for your data set as well. And I will show you some more example of metadata later on. So for the why is it that we need to create the metadata for your data set now? Over time, you can see that when you have your research project in hand, you know what's going on, you memorize everything. But over time, though, the data, your information, your memory is not the best place to keep the data set information. So you want to document it while your information is still fresh in your mind. So when you are working on your data set, it's also a good time to think about what metadata you want to use. So over time, you don't want to lose your data, and data archiving has also metadata to go with it to document versions, what kind of format you use, what software application you use to create your data at the time. When you come to metadata, in your data entry, you may have your own guideline and and metadata standard. Let me see if I can get it back. So in many, when Chris mentioned different repositories early on, each database or repository will have its own metadata standard and guideline. And what are these is the best practice for data entry, like when you create your own data set too. So this will be what are the common terminology, how do you enter the definition of the data, the structure. So this will help you with the consistent metadata recording and communication, not only for human, but for computer communication and data exchange. The use of the standard also support search and retrieval in the data management software and application, and also to facilitate data visualization, like I would show you in some example later on. So some of these, in the following slides, I talk about some example of metadata records. So this one is North American Breeding Bird Survey, the BBS, by the Federal Geographic Data Committee standard. The benefit is that if every geographic data set use this standard metadata schema, then everyone would be able to understand the metadata, and computer would be able to process the different search and facet for that too. Another discipline-specific database, metadata Pangea database, which is the database for data for the earth and environmental science. It requires certain metadata elements. You can see here, for example, event and the expedition, because most of these are ocean drilling data. So most of these you have to go on the ship. So you have the ship information, who's the author, the data set title, reference, the methodology. So these are some examples. You can see abstract and keywords. These are very common, and you can generate this data into your data citation afterward too. Another example from the Pangea metadata standard, you can see in this example that the metadata describe the data, and also it can be used for search facet and filter, as well as for mapping and visualizing data. This is an example of a smear slide data, which is derived directly from the smear slide data collected on board the Gomer Challenger ship. So the ship's information will be in there. So each smear slide represents a small portion of the sediment that distribute on glass slide for microscopic evaluation of mineral and fossil composition. So in the data facet, you can search by the name of the mineral and also the fossil composition. But on the right-hand side at the corner, you can see there's a map there. So the latitude and longitude information can be mapped into Google Maps. So this is another benefit of metadata for data visualization. Another thing that I mentioned earlier about the ORCID, the researcher identifier. Nowadays, most funding agency will ask for your researcher ID. ORCID has been the most common one among the funding agency. For example, in Pangea, not only that you can create and add your ORCID researcher ID, Pangea will also pull your data between Pangea and ORCID, so it has the API that interact with each other. It's the same thing here. I have an ORCID ID in my element, the faculty portfolio. I can add my ORCID ID, and it will pull all my publication from ORCID to populate the data in my faculty database elements that we use at UT. We also have Pivot, which is a funding agency database. I create my account in Pivot, and once I add my ORCID ID, Pivot go live to ORCID and pull my publication data into Pivot without my intervention. And in the future, when you add more information, publication, dataset citation in your ORCID profile, it will send that data almost on the real-time basis to Pivot. So metadata is more powerful now, not just to describe the data, but it's also allow for computer API interaction. So this is some of the benefit that I have to show you about researchers ID. Scopus ID and other ID can be used in ORCID as well. Now, another benefit of metadata nowadays, you can use it for visualization. These are some examples that you can see. There's Smithsonian has a project called Place and Space, and over there you can see some example of different scientific projects that you can with the data visualization. Carto is a popular mapping tool that digital humanities and other researchers can use for map application to plot and visualize as a map data. For example, I have, and there's also a book by Kathy Bernal based on the place and space at the Smithsonian. Another example I have is by my colleague, Dr. David Joseph Risley. He's an associate professor of English at the American University in Beirut. What he does is he creates a project for linguistic landscape of Beirut because in Lebanon, people are using different languages. So the one that he's looking for is the sample of signage in Arabic, English, and French from different Beirut area. He used the mobile app called Fulcrum to take the picture of those signage and plot right into Carto, and you can generate different data point from language and script. And so that's been not only getting the metadata in the image, but using the metadata in plotting and analyzing on the map using Carto as an application. Another example is from the Cornell Ornithology Lab. They have the bird data observation that people from around the world actually can send to the lab. And for example, the metadata in here has the species, date, time, and place of the bird observation. And they use that to generate this map from the bird observation data. So it's based on, this particular image is based on the metadata for Tennessee birding hotspot for the blue herons during the months of March and May this year. So you can really drill down your data and mapping using your metadata. So you can see that metadata can be used in many powerful ways. I hope that I can convince you now that how important metadata is not only for your data set, your funding agency, but from documenting, archiving your own data sets for the future, for sharing the data set with others in your discipline database and websites, but also for data visualization and for populating your data information in your faculty portfolios and your funding database, such as Pivot. So I think that's about my part of metadata. And if you have any question, please let me know. If not today, you can always send me the email. I'd be happy to answer any question on that. And I can, hopefully, I can get this back to Chris now. Hi, Chris.
Okay.
I give up my remote. Okay.
All right. Great. Thank you. Thank you so much, Joy. That was a very informative presentation. So I hope that, like she said, I hope she convinced you that how important metadata is. And I will give everyone's, both of our email addresses later in case you have questions specifically for her. You can email her about it. Okay, moving on. So the last section I want to talk about today regards data citation. Citations of data are similar to citing any published work, like an article or a book that you might use within your research in your articles. It provides information that you need to identify and locate that work, in this case, the data set. Right now, there are no standards about data citation, but there may be a recommended format by the journal that you're publishing in, or the repository that you're archiving your data within, or maybe even within your professional organization. So look into that, investigate it, and see if your professional organization has a format. If not, you can always contact me, and I can provide just a typical data citation format that you might want to use. So here's an example of a data citation from the Dryad digital repository. You'll see it mimics an article citation. It gives you the authors, and the authors of a data set are those who actually collected the data and created the data set. It gives you the date at which it was created, and it gives you the title of the data set. And in this particular example, the data set title is data from landscape level variation, etc. And that is the actual name of the project or the name of the article that the data support. It can be one of the two. And in this case, it's probably the name of the article, because the article, as you see, is in PLOS One. And so PLOS One published the article, Dryad published the data, and then they're linked together by the DOI. The DOI is in this citation is for the data set, and when you go follow that DOI link, it takes you to the data set in Dryad, and then on that Dryad page there is another DOI and citation for the article, which you can click on, and it takes you to the article in PLOS One. So those two things are interconnected. If you go to PLOS One for the article first, it'll also send you back to Dryad for the data. So that's a great way to link up your articles and data sets, so that people who know or find one or the other can always locate the other one. So that is the end of the presentation today about data management best practices, and I wanted to put a plug here for a group of librarians we have in the library called the Scholars Collaborative. We have a scholarly communication librarian, Rachel Caldwell, who can help you navigate issues related to publishing and copyright. We as librarians always encourage you to maintain your copyright on your published works if at all possible, and Rachel can help you navigate that. And then I'm your data curation librarian. Anything related to data management or data sharing, you would want to contact me. Eric Arnold is our GIS specialist, so if you have any need for plotting data via maps in software such as ArcGIS or the open source versions of GIS software, then you would want to talk to Eric Arnold. And then lastly, Michelle Brandon is our media literacy librarian, and she also manages our studio, so she can help with anything related to audio video editing or creating graphics, or if you have a need to videotape something in your research, then she can talk to you about that and help you with that. We have lots of equipment that you can check out as faculty and also grad students that will allow you to create videos and audio and graphics for your research. So if you need to get in touch with any one of us, you can just email that scholarsco@utk.edu email address, and it will get to the right person. So thanks for coming today. This is our contact information is here. If you have any questions, please reach out to either me or Joy, and we're happy to help you with anything related to your data management or metadata. And I do see one question popped up here. Let's see if I can answer that. Yeah, you're welcome. It was just a nice thank you message. So thank you again for coming, and I hope that it was helpful. And here's another question: does UTK offer a free SQL database? Is there a noon biological pure science data repositories that you would recommend? I'm not sure what I know that UTK offers access to Microsoft Access as part of the Office 365 package, although I have recently learned that it may not be a part of the Mac version of that of Office 365. I think it may only be part of the PC edition. As far as free SQL databases, you can always download MySQL, which is, you can download that from their website, and you don't have to be affiliated with UTK. As far as data repositories go for biological pure science data repositories, non-biological pure science data repositories, I would check that RE3 data website and see if you can find something. Let me know if you need some help. I'm happy to meet with you separately and kind of get an idea of what specific type of data you're looking for, and I can help you look through that as well. So just email me if there's a need for that. Okay. All right. And can I share today's materials via email? Absolutely. In fact, the presentation was recorded, so it will be online soon, later today, and I will also send you an email with the slides so that you can have those as well. And it looked like a message popped up, but I don't see any message here, so I'm going to assume that that's all the questions unless you have another. So if there are no more questions, I will end the presentation. Thanks again, and let me know if we can be of help. Thank you very much.